Okay, so we're still in section 1.10 looking at graphs, and this is kind of the second part. So if we look at the graphs of bottom of page 84 and 85, so finish this up. If you look here, it looks like you're paying off a debt here. It looks like student loan debt. So the more time goes on, obviously you're going to make more payments. So the number of years of repayment, notice this is going down. So this is a negative correlation. So meaning as the years of repayment goes up, the amount of money you owe goes down. So that's a negative, and it's definitely linear. Do you see how it kind of looks like a line there? All right, the next one, this kind of, kind of looks linear here a little bit. So not as perfect, but you can kind of see a general trend, right? So yeah, there's always some outliers there, but for the most part, our line would kind of be in there. So meaning the higher the square foot, the price of the house tends to go up. So as one goes up, the other goes up. So they match. That's a positive correlation. But then if you look down here, this one kind of looks more like a parabola, an upside down parabola there. So it looks like as selling price goes up, 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 and up, the revenue the company makes doesn't keep going up. And that's kind of, there's this, if you're a business person, there's this like optimal price. So if it's too cheap, obviously we might be selling a lot of it, but that doesn't bring in a lot of revenue because it's too cheap. There's this optimal price where you can sell it for a certain amount and people will still buy it, so you have pretty good demand, but because you're charging more, you're going to make more, bring more revenue in. But then there's a problem if you up the price, say, to over $50, less people are willing to buy it, so again, you're lowering your revenue again. So again, sometimes there's a maximum, like this optimal price, right up here where kind of that whole supply and demand thing. So that's not linear because it doesn't even look like a line. So there is no positive negative correlation there. It's not linear. All right, so our number 4, there's a bunch of descriptions, and it goes on to the next page. So we'll click over and look at 86. And see if I can go up here. Is there more up there? Oh, I guess it's just a 2. Okay, so then look at these 2, and then there's these 6 graphs. And so what I want you to do is pause the video and try to match what it says to the graph, and then also try to figure out what your independent, so independent is always your X, dependent is always your Y, what the variables are. So figure out which graph goes with which description on these 2 pages, so these down here, and match them to the graph, and then try to figure out what the independent and dependent variable are. So I'm going to have you pause and you try to figure out what graph goes with what. All right, so let's look at these and kind of see what we think as far as what's going on, and maybe start trying to figure out the easiest one first. So I'm not sure which one you guys think is the easiest. This one might be not too bad. If you kind of look here, it's going up and then it kind of stays constant. So if you kind of look at the descriptions for number 6, it's like going up, but then it stays constant. So that looks like A. You save the same amount of money each month. You don't get any interest on it, and then you get a goal, and then you just leave it there. But because there's no interest, it just kind of stays put. So that looks like A goes with this graph right here. And then as far as what your independent, so time is almost always on your X. So your independent variable would be time, and then how much money you have in the account is going to be here. All right, let's look at what else we have. Temperatures in a given location. So, well, we live in Iowa, and right now, this is almost like every day of the week here going on right now. But so we have the seasons in Iowa. So some states wouldn't look like this. But Iowa does, so, we have cold and then gets really hot, and kind of average temperatures gets really cold again, and so forth. So this would be B, the temperatures, at least around here. So again, independent would be time, so that would be months, and then temperature would be on your Y. Let's see what else. Bacteria that doubles every hour. So it doubles and then doubles and then doubles and doubles. that's going to be this guy. So if you start with 1, it's going to go to 2, 2 is going to go to 4, 4 is going to go to 8, 8 is going to go to 16, but eventually it's going to go 32, 64, 128, and it's going to get big fast. This is called exponential growth. And so population of bacteria doubling every hour, definitely exponential. So that's this graph. Your X is going to be time in hours. So 1 hour, 2 hours, 3 hours, so forth. Or they might go, 10 hours, 20 hours, who knows. But they have to be consistent amounts. So like you can't go, like 2, 4, 8, 16. You can't do that. You have to go 2, 4, 6, 8, 10, 12. You have to have a consistent amount. So this would be time in hours, and then the population would be here. So again, since it gets big so fast, you might go 50s, 100, 150, and so forth, and so that's why so many points are together here. All right, the height of a ball after it's shot from a catapult. All right, so if it's shot, it's kind of at ground level, and then over time it's going to peak at a certain height, and then over time it's going to hit the ground again. All right, so this looks like it goes with D. And then, again, time tends to be your X, which is seconds. And then your height is here. All right, so which ones are left here? Which ones haven't we done? All right, the number of days needed to build a bridge compared to the number of workers. All right, so let's look here. So the number of days. So if I only have 1 worker, it's going to take like infinity to build a bridge. If I have 2 workers, probably infinity, 3, whatever. And then if, say, maybe I have 20 workers, then I get some measurable time, like a year or 365 days. But there comes a point if I have 10,000 workers, it might take less time, but really the more workers I have at a certain point kind of is negligible. So that would go with E, and then workers is your independent variables, and time in days would be here. And so the last one, the one we haven't done yet, is this guy. And this is going to go F, the number of students on a college campus who get a highly contagious flu. All right, and then time in days is here. And then what do we have? Number of cases, or number of students is going to be here. So what happens is nobody has it. All right, somebody gets infected. They infect other people. And for a while, it almost looks like exponential, like everybody's infecting everybody. But there comes a point where kind of everybody's, sick, I guess. And so it kind of levels off at a certain point, like everyone's been infected. And so you kind of have, a bunch of healthy people, but they're all getting infected, and then it grows really fast, and then it kind of levels off a little bit. All right, so that's good enough for the rest of the section. On page 87, your homework would be to do 1 through 4 in the book. So page 87, 1, 2, 3, and 4, and then do the online homework too. All right, that's part 2.